Good morning, everyone. It is a pleasure to be here today to present our work entitled Scalable Synthesis and Microstructural Analysis of Turbostratic Carbon via Self-Propagating Magnesium Combustion. Over the next few minutes, I will walk you through how we developed a fast, cost-effective, and highly efficient route to synthesize this advanced nanostructured material. To begin, let us contextualize the importance of turbostratic carbon. Unlike highly crystalline graphite, turbostratic carbon features rotational and translational disorder between its graphene layers. This structural disorder leads to an increased interplanar spacing. This is a key feature because it significantly facilitates ion diffusion and provides a high density of active sites. Consequently, turbostratic carbon is an exceptionally attractive candidate for energy storage devices, catalysis, and carbon dioxide capture. However, traditional synthesis routes present major drawbacks. Conventional pyrolysis, chemical vapor deposition, and graphene oxide reduction generally require long processing times, sustained high temperatures, and expensive equipment. Therefore, developing a simple, rapid, and scalable synthesis method remains of high scientific and industrial interest. In this work, we explore a novel approach based on a self-sustaining magnesium combustion reaction in a carbon dioxide atmosphere to rapidly produce turbostratic carbon, characterizing its microstructure through electron microscopy and diffraction techniques. Moving on to the methodology, shown in Figure 1, the experimental procedure follows a straightforward sequence. In panels A and B, we prepare the precursor by fabricating metallic magnesium wafers, 2.5 centimeters in diameter and 1 centimeter thick, using a die under minimal manual load. Next, as illustrated in panel C, we initiate the reaction by placing the magnesium inside a carbon dioxide environment and igniting it using a graphite electrode powered by alternating current from a commercial arc welder. The self-propagating combustion reaction rapidly reduces CO2 into elemental carbon within seconds. In panel D, we observe the complete consumption and cooling of the metallic magnesium. Finally, in panel E, we purify the product by immersing the resulting pellets in a 20% hydrochloric acid solution to leach out remaining magnesium oxide impurities. Now, turning to the results section, we evaluated the structural and morphological features of the synthesized carbon. In Figure 1A, the scanning electron micrograph shows an irregular cluster morphology composed of stacked sheets. In Figures 1B and 1C, energy dispersive X-ray spectroscopy and elemental mapping confirm carbon as the predominant element, showing minimal residual magnesium and oxygen. At the nanoscale, high-resolution transmission electron microscopy in Figures 2A and 2B reveals a clear nano-onion-like morphology made of concentric spherical structures. This geometry provides high structural stability and a large surface area. Furthermore, Figure 2C illustrates the indexing of the characteristic D002 interplanar spacing at 0.35 to 0.36 nanometers, which is larger than that of ideal graphite, confirming the turbostratic nature of the material. These findings are corroborated by X-ray diffraction, which confirmed a turbostratic hexagonal structure belonging to the P63MC space group, with an average crystallite size of approximately 8 nanometers. Furthermore, Quantitative analysis showed a low residual magnesium content of less than 3 atomic percent, demonstrating the high conversion efficiency of the combustion process and effective acid leaching. In conclusion, turbostratic carbon was successfully synthesized via the self-propagating combustion of magnesium in a CO2 atmosphere. SEM and HRTEM analyses confirmed a laminar morphology with nano-onion structures and an interplanar spacing of 0.35 nanometers. This technique offers a simple, rapid, and scalable route to produce high-quality carbon materials tailored for energy storage and electrochemical applications. We would like to acknowledge CHIDI and Nanotech CMAV for their technical support. Thank you for your time, and I am now open to any questions.